This is a tutorial for the design of vertical ground source heat pump systems using the software GSHPCalc. The design of these systems is not difficult, but gathering the needed information requires knowledge of building cooling load and heat loss calculations, ground formation, thermal properties, equipment performance, and methods of ground heat exchanger construction. We will begin by entering here and agreeing to the conditions. The most time-consuming portion of GSHPCalc is the input of the building cooling and heating loads. Preliminary design can be performed with the building's totals as shown on these two rows, which summarize the totals for different time periods for the entire classroom wing. This is for cooling, and these totals are for heating. However, entering the zone-by-zone information will permit the appropriate heat pumps to be selected for each zone. For this tutorial, a school wing with 10 classrooms located in Sacramento, California will be used. It's north-facing. So let us begin. This is the first screen for Zone 1, which corresponds to Classroom 101 in this drawing. So we will enter the cooling loads first. We'll see in the morning in room 101, which is Zone 1, is 28,000 BTUs per hour. In the afternoon, the load is 30,000 BTUs per hour. In the evening, it's 12,000. And at night, it's 8,000. This zone here is a method of accounting for keeping track of how much heat goes into the ground and how much heat comes out of the ground on an annual basis. We need to know this to minimize the amount of long-term temperature change. This program uses the method of results of an ASHRAE research project that provided the equivalent full load hours for a variety of building types and locations throughout the United States. These values can be found by clicking on this button here. Now, however, we have looked up the values for a school in Sacramento, and the equivalent full load hours is 890. This is the number of days occupied. It's a school, so we're using 5. If the school has activities on the weekends, this number could be bumped up a little bit. We'll then go to the heat loss values. We'll see down here in the morning, usually the peak period is 26,000. In the afternoon, it's 12,000. Evening is 8,000. And at night, it's 10,000. The equivalent full load hours in the heating mode is 360 for Sacramento schools. Okay, now we can take the values in this particular zone and apply them to other zones which have the same load. So you can see these 4 zones, and this one's a little different, but it's close. So we'll go ahead and click the zone window, and it gives us a message to select F3 at the top of the keyboard. So when we do that, we can copy the zones, the values in zone 1 to zones 2 through. Now I'm going to go ahead and put 105 and 106 in there, which is zone 6. And we'll change these two when we get to them. Okay, but these 3 here will be the same. So we'll hit the return button, and you can see the values in zone 1 have been put in 2, 3, 4, and 5. Now we'll go to zone 5 and change the things that are different. So it's 30,000 for the cooling load in the morning, 32,000 in the afternoon. At night, it's 14,000, and in the evening, it's 8,000. No change. All right. So then we go to the heating for zone 105 or zone 5, and it's 32 in the morning, 15 in the afternoon, 10 in the evening, and 12 at night. Then we'll skip to zone 6, which already has some information in it, and we'll again change what's different. Okay, so zone 6 in the morning is 22. Okay, so this is a west-facing window or classroom, so the load in the morning is smaller than it is on the east. In the afternoon, it jumps up to 36. In the evening, it's 8. I'm sorry, 8, it's 16. And at night, it's 10. Skipping over to the heat loss, it's 26, same, in the morning, 12, 8, and 10. Okay, so it's same numbers. Okay, so then we'll take this information that's in zone 6 and put it into the other zones. Click there, hit F3, and we'll copy from zone 7 to zone 10. And we'll see that the information in zone 6 is the same as in zone 7, 8, 9, and 10, and we'll change what's different in 10. So in the morning here, the cooling load is 24. The afternoon is a little bit higher, 38. In the evening, it's 18. And 10 at night. The heat loss is 32 in the morning, 15 in the afternoon, 10 in the evening, and 12 at night. Okay, this completes the data input. So we're well on our way. So we're going to go ahead and save this information into a file. Okay, so I'm going to change this. I'm going to go ahead and call it 6. This is the 6th try. So we'll call it 6 and save it. And we'll hit the next screen again to go back, and that will ask to save us again. So now we begin the design of the ground loop itself. Okay. These two numbers here, this is the return temperature from the ground loop in the cooling mode. It enters the heat pumps, and this is the temperature in heating that enters the heat pumps from the ground loop. And this is the flow rate. So what these notes down here tell us is that a good starting place and for the design is somewhere 20 to 35 degrees above the ground temperature, which is 62 in this case. So if we added 35, this number would be 97, and that would not be a very efficient system. So we're going to add, let's round it up to about 85 is a good number. That would bring us about 23 degrees above the temperature of 62. Over here on this side, we can see that this load here, the cooling load, is greater than the heating load. So what we'll do is just bring this up about 10 degrees rather than 15, or down. So we'll drop it from 62 down to 52 degrees. Okay, and the flow rate we'll leave at 3 GPM per ton. You can go down to 2.5. That's usually pretty good on these closed loop systems, somewhere between 2.5 and 3. Go to the next screen. This screen contains a lot of information from equipment manufacturers, a series of heat pumps, and these heat pumps have been corrected from their rated values to values that are experienced in the field. Two of the things that are important are the return air temperatures are rated at 80.6, which is not a comfortable condition, so we'll change the values, the performance, using an entering temperature and cooling of 75, and we'll use 70 degrees rather than 68 in the heating mode. Even more important is that the ratings have very little information about they don't contain power used by the fans to any large degree, so it must be entered so that we correct these heat pumps and get the proper performance. And so all of these have been corrected for those two things. Okay, so now we're going to select a series. We're going to do kind of a middle-of-the-road heat pump. We'll pick this one right here. And it's a Climate Master Tranquility 20. We'll open it up. And you see what's happened is the program has selected heat pumps to match both the heating and cooling load requirements. And so in these 4 zones, you'll need a 3-ton. And in this corner zone, it'll have to be a 3.5-ton. And all these zones here on the west side will need the 4-ton unit. Okay? And it tells us what the flow rates are in both English and metric unit. The program does both international and U.S. units. So we'll go to the next screen, and we're going to use, there's 3 options here. We're going to design a vertical closed loop system. You could also do a groundwater system with this software, or surface water. But of course, this is for the ground source, so we're going to call this, give it a name. You could put a lot of other information here, and it will print out. So we'll call this Sacramento 10 class. Okay, so then we'll select vertical ground loop. We're going to enter new information for the ground loop. So here we have this is from the terminal property test that's recommended that's performed before construction begins or design begins. It says the ground temperature 62, so that's already in here. The thermal conductivity is 1.3 BTUs per hour foot degree F, and the thermal diffusivity is 0.9 square foot per day. Okay, and there's a lot of other buttons you could get to get more information, and there's also a button for recommendations for doing the thermal property testing. Go to the next screen. Here's where we tell it something about the vertical heat exchanger. The driller is drilling a 5-inch hole in the ground, and using 1-inch high-density polyethylene. And the standard grout that this driller uses has a thermal conductivity of 0.9. The pipe is DR11, which is the standard dimension ratio used in most ground loops. Now, the flow is turbulent. This is a cooling load calculation for design, probably. The water entering the heat pump is 85, comes out about 95, so it's going to be very low in viscosity at those temperatures, and so the flow is likely to be turbulent. I want you to notice that when you go from turbulent to, say you select a transition, you see it doesn't change the value very much. Okay, there's turbulent, there's transition, and there's laminar. You see laminar goes up a little bit. So transition, turbulent. Okay, so now we're going to assume the BC arrangement where the U-tube is on near the wall of the bore, which is typically where you'll find it when it winds down the tube. So here we go. You can, of course, use non-standard pipe or non-standard values for the heat exchangers, and in that case you would just type the value of the bore resistance that you get from some other calculation method. So we're going to go forward with the next screen. This is the screen where we enter the format, the layout of the vertical grid. This is right around somewhere between 25 and 30 tons, so we're going to try to get a grid with around 1 or a little bit more than 1 bore per ton, because the driller can go to 300 feet. So what we're going to do here is we're going to do a 4x6. Now the reason we're doing 4x6 rather than say 5x5 is because these U-tubes have to be arranged in circuits. A circuit being something, piping that comes either from the building in a larger diameter pipes with 6, 8, 10, 20, not up to 20. 20 is a little high, of U-tubes on a single circuit. So if we do a 4x6, you see you could have 4 circuits with 6 U-tubes on each circuit, or you could have 3 circuits each with 8 U-tubes, or 2 circuits with 12 U-tubes. Whereas if you had 25, a 5x5 grid, your only option would be 1 circuit with 25 bores, and that's a little too much. Okay, we're going to separate these bores by the minimum recommended distance of 20 feet. We're going to use 1 bore per loop, which is 99.5% of the time this is what you're going to be using. In some cases where you have very, very shallow drilling conditions, you may want to design a system where you put 2 bores in series so that you don't have too many parallel paths and get into flushing and laminar flow problems, or 3 bores per loop. This is rarely done, so we're going to go with 1 loop. It's also very difficult to flush with these kinds of arrangements. So we're going to go with 1 bore per parallel loop. Go to the next screen. Now, we're trying to do ground source heat pumps to make systems very efficient. And one of the things that individuals do is they just put too large of pumps. And since this is a very efficient system, if you oversize the pumps, then the system efficiency will be negated. So what we're going to try to do here, this is a very small loop, so a good engineer should be able to get by with about 40 foot of head on those ground loops and interior loops. Okay, so we can see when we do that, we get a 1.2 horsepower motor required with a 70% efficient pump. And then if we wanted to know what the typical efficiencies for, in this case we'll have to have a 1.5 horsepower pump, we could click on this button and it would typically tell us the efficiency of the motor. Okay, so let's go to the next screen, and this is where we look at our results. Calculate the bore lengths, and we can see in this situation we stayed below the 300 feet that the driller likes, 297 feet and 24 bores. We can see down here that we have, this is if we have a formation we're not familiar with that may have a lot of clay and not much water, and low porosity, so that the heat buildup over the 10-year period of which this calculation is performed would require a little bit longer bore. Now, if you were in an area, for example, on the Gulf Coast where they do a lot of these, they're drilling in wet sand, and so the long-term heat change, because of all the water and the movement and the, in some cases, evaporation of the water, keeps the long-term temperature from changing much. So in this case, you'd only need 265 feet of bore to keep the temperature at 85 after 10 years, okay? Which is pretty much the same as in year 1. Down here we have the information about the loop temperatures. You put the entering temperatures in at 52 and 85, and then these are the calculated outlet temperatures along with the temperature that you entered for the ground. Here's the information you put in about the ground heat exchanger and the ground itself. Okay, so we can see the results show us that we have a heat pump EER of 14.2 at worst case, and if we include the pumping, it's 13.6. So we did a good job of keeping that pump power down to where it didn't mess up our EER and our COP. COP is 4.5, very good, very good. And the system is 4.3, and we need 84 gallons a minute and 40 foot of head from our pump. Okay. Now we could stop here if we were happy. Another thing we could do is say, let's try to see if we can get some better results using improved grout. So remember this number 297, and so we'll go to the next screen and we'll go into this button here and change the grout to 1.2. Okay, and that will cost us an extra 50 cents per foot on the bore. Okay, so we then go back to the next screen and calculate the bore length, and you see we dropped that number 283 from 297. So basically what you would do is you would take and multiply 283 times 15 plus 50 cents, or 15 and a half, to see what the cost would be. And then you would compare that with the 297 times the $15, which was for the 0.9 grout. And in this case, I think the 1.2 would win out and give you a little bit better, a lower cost. Okay, now let's don't stop here. Let's see what happens if we wanted to go and pay some extra money for a heat pump and get something that was more efficient. Okay, so then we'll go back to the next screen and we select heat pump model. Okay, so we're going to load all the data, and we're going to go in and we're going to find us a higher efficiency rated heat pump, which it doesn't show it on here, but you should be able to find that from the rated data from ASHRAE. So I'm going to click on this one here, a little more pricey, open it up, and it's more efficient. You can see what happens. It's got the nominal capacity of the 3-ton unit allows you to put 3-ton units in all 5 of these zones and 3.5-ton units in the west-facing zone. So let's go to the next screen and we will calculate the required bore lengths. Okay, so we did several things. We dropped that from 281 down to 275, a little bit of a change because this machine is a little more efficient, doesn't dump as much heat into the ground. But the big thing is that we increased the EERs quite a bit, from 13 point something up to 16, and from 4.3 up to 4.6. Still have 84 GPM. So we would have to do an economic analysis to see, is it worth spending a little extra money on these higher rated machines. There are many other things you could do. You could change the heat exchanger design. You could move them further apart. You could let the temperatures rise up a little bit more in cooling and drop down a little bit more in heating to see what that would do to your efficiency, and that would of course change the cost. You could also, although I don't recommend it for schools, do a hybrid system. In that case, what you would do is when you go in, you would add this temperature. You might want to drop it down to, say, 45 degrees. And what that would do would make the length required for heating quite a bit shorter. And then you could go here, which of course it wouldn't cover the cooling load. So to keep the temperature down, the cooling load, you click on this design hybrid, and it would tell you what size cooling tower you would need to put in parallel with the ground loop to keep the temperature at 85 degrees. However, again, I would not recommend doing this at a school. Cooling towers require quite a bit of maintenance and care to keep them not only operating correctly, but operating safely. So schools typically do not have the resources to hire maintenance personnel to do this. So 100% ground loop is an ideal thing for a school. So with that, we'll cease our operation of this program, and hopefully it will give you a great deal of assistance in preparing others. In the future, we will also have some tutorials for surface water heat pump systems and open loop heat pump systems. So hope this helps.